Alright, this is out of the book 3.4, example 4, page 126. It says a dynamic blast propels a heavy rock straight up with a launch velocity of 160 feet per second. It reaches a height of this. That's our equation. That's our height equation after t seconds. Okay, so this is our equation. S represents height. Generally, in calculus, S is position. Okay. So it could be H, but here it's S. So first question, how high does the rock go? Well, what we know is the rock goes up and then it goes back down. Okay, so we know that when it gets to the top, what is true about the velocity? Right there. Well, we're only talking about vertical velocity, so imagine it goes up, it's basically stopped, and then back down. So this is height versus time. So how high does the rock? We know that it goes to here, and the velocity must be 0 at that point. Okay, it's got a horizontal tangent, so the derivative of s, which is velocity, so the derivative is 0, so velocity is 0 at that point. So we're going to find ds dt, which is the velocity. Find the derivative, 160 minus 32t. So that's my velocity equation. We can find when the velocity is 0. That'll give us our horizontal tangent. Divide by 32 and we get 5. Okay, so this right here is 5 seconds. How high does it go? Well, we know when it's there. Now we can just find the position at 5. So we can find S of 5 equals 160 times 5 minus 16 times 5 squared. What's that? 800 minus 400 gives you 400. So how high does it go? It goes 400 feet. This is 400 right there. Part B, the velocity and speed when the rock is 256 feet above the ground. So if that's 400, this might be 200, 256, like right here. We know it's going to happen right here, and it's going to happen right here. We want to know the velocity and speed when that happens. Okay, so first of all, we need to know when it happens. What do I know 256 feet is? That is the height, or the position. So we'll plug that in for S. So 256 equals 160t minus 16t squared. We can solve. I'll move everything over here. I think everything's divisible by 16. Factor. Oops. So I get 2 and 8. So right here is 2 seconds, and right there is 8 seconds. Okay, we want to know the velocity at that point. So on the way up, the velocity, well, we can plug in 2. The velocity at 2 is 160 minus 32 times 2, so 64, so 96. So on the way up, we have a velocity of 96 feet per second. So the velocity of 2 is 96 feet per second. Okay, what about speed? The speed is always the absolute value of velocity. Speed can never be negative. Okay, well, the velocity at 2 is 96. So then the speed at 2 is also 96 feet per second. Alright, so what about on the way down? We can find the velocity at 8. Velocity at 8 is 160 minus 32 times 8, 240, 256. So that is, what did I say, 240, 256. So negative 96. So the velocity on the way down, or the velocity at 8, is negative 96 feet per second. And then the speed on the way down would be positive 96 feet per second, because you can never have a negative speed. Alright, I should have used a different color, sorry about all that. Alright, so what is the acceleration? Well, we know that the velocity is 160 minus 32t, so then my acceleration would be just negative 32. Okay, derivative of velocity is acceleration. And that makes sense because we are in feet per second for our initial speed and velocity, so the acceleration of gravity is negative 32 feet per second squared. When does the rock hit the ground? Well, we know based on the symmetry of the parabola, since I started at 0, 0, 0 is it's a y and an x intercept, so this would have to be, if the midpoint is at 5, then I know that it's going to hit the ground at 10 seconds. If we wanted to just double check algebraically what is true when it's on the ground, that means that the position or height is 0. So we could set that equal to 0 and solve, and we should get the same answer. Take out a 16t, I'm left with 10 minus t. So set them equal to 0, we get 0, and we get 10. So it's on the ground at 0 and 10, and our sketch is pretty accurate. 10 seconds.